Well, first of all, a warm welcome to everyone who showed up here at Skylab today, where we're streaming from. And also a warm welcome to everyone who's joining us outside of Skylab. We're streaming via AI Denmark, so welcome to you as well. We hope that you enjoy your lunch with us, and it's going to be an intellectually stimulating one of the kind. So my name is Camilla Nørgaard Jensen. I'm an innovation manager here at Skylab and also with the Pioneer Center of AI. And we're super excited to bring to you the second applied AI talk of the fall. We're going to have more in the spring, and we have 2 more coming up later this fall. So we hope you'll join us for those as well. There's a QR code behind me on the slide, so you can sign up. And as always, there's the option to go online or to join us here in Skylab. So today we are bringing together academia, startups, corporates around a shared interest of applied AI and what it can do for business and for society and the impact it can have. So it's for everyone who's curious about AI. And we're excited today to welcome back home, you could say, to alumni of DTU. So first we're going to hear from Muhammad Filfil from Paragit Solutions. He's going to share with us about how they worked on a solution to help patients with Parkinson's. And second, we're going to hear from Tulin Schøler from from BrainCapture. And we're going to hear about how AI can be helpful in degenerative disorders. Good. Without further ado, Muhammad, please take the stage.
Thank you. Thank you. So it's a pleasure to present to the current challenges associated with Parkinson's, as well as highlighting some of the interesting results that we have obtained during the establishment of Paragit. So I'm here representing Paragit Solution. It's a medtech startup specializing in development of advanced wearable textile technologies and software algorithms to take the raw data and translate them into insight, objective data for Parkinson's. So who are we? My name is Muhammad Filfil. I'm the founder and CEO, and I started Paragit back in 2018 while I was studying in electrical engineering at DTU. And then when I received my diploma back in 2019, I went full-time. And today we are 7+ people, 8 people, working on a common mission, having very strong clinical collaborators, partners in hospitals and regional hospitals around Denmark, and as well having a very strong and dedicated chief operating officer as my co-founder. And then we are guided by some, I would say, experienced advisors within drug development of Parkinson's and as well as neuroscience. So just small facts about Parkinson's for those who don't know about it. Parkinson's is a neurodegenerative disorder. It affects approximately 10 million people worldwide. It's the fastest growing one. It's the second largest one right after Alzheimer's. And it's accumulated billions of euros of economic loss, both in treatment and loss of labor. The symptoms that are associated with Parkinson's are the one that you probably know from Muhammad Ali or Michael J. Fox. It's shaking, called tremor, bradykinesia, slow movement, and rigidity, muscle stiffness. Those are the ones that are the motor symptoms of Parkinson's. Of course, there's also the non-motor ones, but we are targeting and focusing on the motor symptoms only. So there's actually a huge problem when diagnosing and disease managing Parkinson's. It's unfortunately based on a subjective standard scale called MDS-UPDRS. It's when you go to your doctor and you feel some stiffness in your arm or you feel some small shaking, then your doctor will probably refer you to a neurologist. That will take a year to 2, depending on where you are in Denmark, for instance. And then they will ask you to perform finger tapping tests. They will feel your arm, how stiff it is. This is the way of diagnosing, by the way, and then also managing Parkinson's. There's unfortunately, due to the subjective nature, it results in a very high misdiagnosis rate. Because also of the late intervention with the doctor and neurologist, you often lose up to 70% of your dopamine neurons, meaning that most of the drug compounds won't have much effect afterwards, and it will be very challenging to manage that. And just alone, 75% of Parkinson's patients are actually suboptimal treated. So there's a huge challenge associated with it. This is our solution at the moment. We are, as I mentioned, a wearable device company that have produced the wearable sleeve that can capture electrical activity from the forearm and kinematics as well as hydration. And then we are feeding that to our software algorithm that actually translates the raw data into actionable insights that quantifies, as I mentioned, tremor, bradykinesia, and rigidity. So the technology is actually applicable to improve personalized treatment and improve the quality of life for Parkinson's patients. It enables 100% remote telemedicine because you can simply send the sleeve to the patient. The patient will be able to take the sleeve on and the data will be transmitted to a secure cloud system. As I mentioned, it's scalable and good for early intervention because we monitor the electrical activity from the forearm. And it can also improve clinical trial and research by providing objective data on how drug compounds affects the muscular tone. Just to give you an example of what exists on the market, what is used, and some of their strengths and weaknesses. So the kinematic-based one, you can imagine like the smartwatch, Fitbit, another one. They can quantify how much you shake. A smartphone can do the same, but it lacks discriminative power. It's good for the scale. You can simply give it to the patient, they will wear it on, and will have an idea of how they actually have their symptom is progressing. On the other hand, if you want to utilize electrical devices that with wires and electrodes to monitor the muscle activity, it's not made for in-home use. It's very noisy and it's not scalable as well. So we take best from both worlds and combine it under one umbrella and combine it with an advanced software algorithm that can actually translate the data into meaningful insight. So this is just to give you an example, what we see, how the muscle fluctuations are. It's actually in a very high resolution and high sampling rate. This is our target goal with the sleeve. And we look at it as a QR code for perhaps hidden disorders. You can imagine every time you contract your muscles, it will look different from patients that are actually suffering from a neurological disorder. And we are feeding those information data with good label data into our model that can actually give descriptive insight of how the patient are doing and how they are responding to certain treatments. And of course, utilizing some deep learning approaches, we can actually, with big data, be able to predict the offset and the onset of the symptoms. This is just to give you an example of how our model works. At the moment, it's based on a static threshold model. So meaning that when Parkinson's patients have tremor, they shake between 3.5 to 7 times per second. Bradykinesia, which is the slow movement, is if the arm is moving less than 5 degrees per second during the day. And muscle stiffness, if you have an abnormal increased muscle tone during rest. These information are fed into our model, and we are definitely looking at the spectral form of the muscle activity. And then it highlights 3 stages of the symptoms and also their correlating severities. These data are actually fed into our, as I mentioned, the MDLab platform that translates the data into actionable insight. Another example from a case study with D2 utilizing CNN, a convolutional neural network, to detect the onset of tremor, for instance. It performs to a certain degree better than our static algorithms, but again, improving the data quality, giving more labeled data and more data will actually increase the sensitivity as well as the accuracy. Another case example, just to give you a highlighting of what we are doing. This is a case example from Odense Universitetshospital. A patient were having their symptom and they're actually crossing for each hour how they felt in their diary. And our algorithm were able to, with very high accuracy, flag out when the incidents were happening during that day. We also tried it with different kind of machine learning models with multiple instance learning. We tried with support vector machine and nearest neighbor and random forest. They're good for bad labeled data, but imagine when you give sensors to patients that are living in the wild setting, they can do everything. Like for instance, brushing their teeth could look like tremor. So you need to have robust algorithms that can filter out the noises from the real data. This is some of the correlations that we have achieved with our clinical partners at Odense Universitetshospital. highlighting our accuracy towards the neurologist. So when the patient was visiting the neurologist, they had the sleeve on, and while they were examined by the neurologist gave a score, and the patient also gave a score of how they felt, and our software did the same. And we achieved, I would say, good correlations, but again, it's only on low sample sizes, 7 patients only. This is an interesting one, because this is where we can actually be able to predict the offset of the symptoms. Again, the patient were crossing how they felt each hour, and because of the electrical activity that we are measuring, like the smallest electrical fluctuations, we could see an unbuilding tremor that happened before the patient even noticed that. So the potential is big, because imagine if you can actually shrink that sleeve into, let's say, a patch, then the functionality will be something similar to a glucose meter. Like, it will alarm the patient before the symptom will occur to take their medications. This is another interesting aspect. This is where we collaborated with Aarhus Universitetshospital in a procedure called deep brain stimulation. This is where you put electrodes inside the brain, and then you adjust a couple of parameters to put electrical activity inside the brain to attenuate the symptoms of Parkinson's. We did the same thing, a test set up where the patient was wearing the sleeve, and then we looked at the abnormal muscle activation during rest. When we disabled the oscillator, we could see an upbuilding muscle tone 8 minutes after the device was shut off. And this can be used as a proactive feedback system for instance, deep brain stimulation. This one can be used, this was another case example with, let me see, it was also in de novo stage, a patient that was recently diagnosed with Parkinson's, didn't have visible symptoms, but was put in a very expensive PET scan that actually revealed there was loss of dopamine in the brain. So we gave the patient the sleeve and monitored it for 24 hours before and after medication, and we could see also an upbuilding muscle tone uprising towards how they actually felt. And this motivated the patient to start their medication again. So this was a very quick introduction about what kind of results that we have obtained so far. We are looking for very dedicated AI developers that want to join us in our journey. And if anyone want to see our results and technology, you're more than welcome to pay a visit at our office in Frederiksberg. So yeah, thank you. And let me know if there's any questions I would more be able to answer.
Thank you so much. Do we have any questions in the room? I think we'll go with them first, or
yeah.
Alternatively, we'll go for online questions.
Just about
teach.
Sorry, what do I do? So it's about the teaching of your neural network. This thing of comparing non-affected and affected and so on. How big a data set do you need for that?
So we have calculated that we need approximately 80 patients in order to achieve it. But again, at the moment, we believe that 80 patients would be sufficient. Having control groups, healthy control, same age, at approximately 80 patients will be enough to achieve the same accuracy as our static threshold models.
80 patients or 80?
80 patients times 24 hours.
Okay.
Yeah.
Yes.
Thank you for interesting presentation. I was just curious, where do you experience the greatest problems with this? Because now you showed us where you have all the alignments and where you're progressing, but what is the challenging about this technology?
The challenge about this technology is actually differentiating common noises from the symptoms. Not in the signals, but more in the output. For instance, the patients or our model were actually providing too much false positives. So if the patient were actually having the symptoms or not, or maybe they couldn't detect it. So this is the challenge, adjusting the models to actually fit the patient's experience and the neurologist as well. So it's two worlds that we have to compare against.
Do we have other questions? Yeah? Cool.
It was a great presentation. Thank you. The patients, do they have access to the information you're getting?
Yeah.
Directly?
Yeah.
And how can they monitor it, or is it just from your side?
Sorry, say again?
Can they monitor that information?
Yeah, we send them,
use
we
it
are
in-
updating them in the loop all the time. So whenever they take the screenings, we provide them with a report about their symptom fluctuations. And some of them were actually motivated to start their medication adherence again because of the data.
Thank you.
Thank you very much. I'm not expert in Parkinson's disease, but would you get less false positive if it was placed on the legs?
So this is another kind of symptom we can monitor as if we put it at the leg, because that's also, this is called freezing of gait. For instance, when the patient are walking and then suddenly they freeze, we look at the abnormal and increased muscle tone when there's no movement. That could be a possibility, but again, we have also achieved good correlations just by having on the forearm. But we're also exploring it on the leg as well.
Are you planning any long-term studies to better understand if your technology can help to predict a long-term progression of Parkinson's?
Definitely. This is one of the core challenges because how do you know if patients will actually develop it? That will be based on genetics. It will also be based on the predisposal of them. But we are thinking about doing a public study involving hopefully producing around 1,000 sleeves and distributing around in Scandinavia and obtaining as many features as possible in order to cluster potential upcoming Parkinson's patient. But it's definitely a very interesting case. It's also a bit challenging because one of the things is that, yeah, you will be able to, let's say if we can differentiate between controls and upcoming Parkinson's patient. There's also a bit resistance in the business model. Who would benefit from that as well? I would definitely see there's a value in it, because if I was a person who had thought that I might develop, I would rather know that rather than being surprised in a couple of years. Yeah.
Because there are some really invasive treatments for Parkinson's, so I was thinking that maybe that could really help to inform treatment choices for patients if they have a better understanding of what their short-term risk of progression is.
In that, could you just repeat the question?
So some of the treatments for Parkinson's are quite invasive.
You like the deep brain stimulation?
Or like
the DOPA?
duodenum, yeah. And I wonder if patient had a better idea of what their shorter term progression risk was, then they would be more likely to take certain treatments or consider certain treatment options.
So when I talk with patients, one of the things that they wish to know if they had the diagnosis earlier was to change their lifestyle. Because one of the things that is a bit scary about Parkinson's is that you don't need to have it in your family to develop it. It can develop by environmental factors. So changing the lifestyle was one of the things that many patients wish they knew, so they could actually decrease the progression of Parkinson's. So I don't know if that answered the question.
Yeah, no, that's helpful, thank you.
Perfect. Let's hear from Christina. Are there any questions waiting to be answered online? I'll give you the talking stick.
Thank you very much. We have one question from the chat. It's Kiera Capra who asks, how do you differentiate Paragit from waist-worn devices? And why yours are better than the waist-worn?
Yeah, so I assume the person means the kinematic-based one, the watches and so on. We measure the electrical activity, meaning that we have a high discriminative power. We can observe when the muscle tone are stiff or not, and which the kinematic-based one doesn't reveal any information about. This is our key differentiator. And our key differentiator with other wearable textile technology is that this is made for in-home use, 24 hours, without any noises, without any artifact, and providing high quality data. This is the main differentiator.
I can see there's a follow-up question. How do you deal with false positive in the trimmer algorithm? I mean, how do you differentiate between whether the patient is brushing their teeth or whether they are having some tremors?
This is a very interesting question, because combining the sensor input from electromyography and kinematics, we can actually have a higher discriminative power against things that are voluntary and non-voluntary, like brushing the teeth or actually having the tremor seizure. So we combine different sensor inputs. This is the primary thing. Yeah.
No further questions from the chat.
Your Honor. So I actually have a question. It seems like there's so many diseases or conditions that have to do with muscle contraction. Yeah. Are there other use scenarios that you're exploring? Definitely. We have compared different kind of so we can actually differentiate between, just on the muscle zone alone, between Parkinson's patient and essential tremor. We could also differentiate between patients that have cerebral palsy just based on their muscle function. And we're also exploring ALS, Huntington. Disorders that affect your muscles are certainly things that we are tapping into. So yeah. So how come you chose this as the first beachhead market, if you will?
Because Parkinson's have some. It's a market that is easier to see how the medication response is. For instance, so if you give the sleep, we can definitely see on the muscle zone how the patient are affected by, let's say, levodopa, the medication they take. And I would also say, because of Lumbic and the case competition with Lumbic back then, was the starting point with Parkinson's. So our beachhead is Parkinson's, but we're going to expand slowly towards other neurodegenerative disorders.
And you're touching upon the case competition. So I know that you had an interesting journey from when you started this at DTU.
Yeah.
And could you share a little bit about how you thought you were going to do something completely different, and then through partnerships and so on, you ended up on this path?
So originally the idea started back then when I was very interested to see which kind of muscle group I was activating during exercise, and having feedback as things to optimize my exercise. But then there was, as you mentioned, there was a case competition with Lumbic of how to assess Parkinson's patient and all the cardinal symptoms of patients from their own home. And then we did some in vivo tests with volunteering Parkinson's patient, and we received some good results that actually motivated us to take that path instead. And then when we worked with it and we actually met more patients, it was a clear mission for us to actually continue that way. And then we partnered up with different hospitals that saw the value in acquisition of EMG and kinematics. And then, we are actually building the company based on that.
Very cool. Thank you for sharing that story.
Of course.
I just want to check in, are there more questions that are emerging in the audience here at Skylab or online? Okay, Then I think it's time to say thank you very much.
Thank you as well.
Give you a big hand.
Thank you very much for inviting me for this session. To tell you a little bit about what we in BrainCapture are doing with AI, and also slightly more in general. So BrainCapture is a medical startup, very similar to our previous speaker here. We are specializing in epilepsy diagnosis with some equipment, medical equipment we're building for this. And I'll tell you a little bit more about that, but before I do that, I will like to, since we're doing AI, I'll tell a little bit about my background. Is that I have a background here from DTU in machine learning. I have a PhD in machine learning from IMM. I've been working with AI and machine learning for the last 20 years maybe in many different companies, among those in a bank who have implemented algorithms and put them into production and figured out what are actually the difficult things of getting these AI things working. And I'll share a little bit more about my thoughts on this later, but one of the main things is not so much actually building the algorithm. That is fairly easy. Another thing is getting to work, getting to run, getting to be stable, and actually implementing in real life applications. We also have in our founding team another figure that you probably know, Lars Kai Hansen, from the professor at DTU. He's one of our co-founders and one of the guys that got the ideas for this thing, along with Dr. Farah Martin, neurologist from Harvard. But first, let me use a few slides on what epilepsy is. I think you probably all have some kind of vague idea that is something what you can get a disease. You'll shake, fall down, have some kind of seizures. And all of this is actually stemming from the brain, from some kind of disorders. It can be either sort of a specific point in the brain that sort of starts that thing, or it can be sort of more diffuse all over the brain. And it can be many different things that can happen. That it can be some of the big seizures where you see people shaking, falling down. It can also be just freezing mid-sentence, for example. You just stop talking. This happens a lot with kids, for example. So some kids, when they're in school, they'll just zoom out for a while. There's another company that's making a little lamp you can put on the head, so turn on. Now this kid is not working right now, so it's working again. Now we can talk to him again. But there are many different ways it can affect. And this thing with the flashing light is also one of them. It's not so common. It's only 1% of the epilepsy cases, but it's very known because of the Nintendo. And when you see the television, things that can affect a lot of people at the same time. But it can be many different things. And a lot of people, I think 1% of the world's population will have epilepsy in their life. It's 50 million people, something like that. And like is the case in general, 80% of these people live in low and middle income countries. This is actually the same percentage almost as for the general population. And all of these people do not have access to, not all of them, a lot of them do not have access to diagnosis for various reasons. One of them is that the EEG machines, they are currently very expensive. So medical grade EEG machines are super expensive, $1 million kroner, something like that, maybe a little less. There are very few neurologists around the world. In some of these countries, where we're working in Kenya, there's 50 million people. There's around maybe 10 board-certified neurologists for that entire population. So they cannot get the correct diagnosis. And this is a shame, because for a lot of people, if they're diagnosed with epilepsy, they can actually be symptom-free by using cheap, available medicine that's been off patent since the 50s. So there's actually a potential treatment if we can diagnose it. On the other hand, if you take this medicine without having epilepsy, it's actually have some really bad side effects. So you don't want to just give it to everyone that way you think that could be symptoms of epilepsy. There can also be many other reasons that you have these seizures that are typically a symptom of epilepsy. It can be fever, tremors, or it can be there are a lot of other reasons why you can have these symptoms. Epilepsy is a huge problem for kids also. So a lot of the age distribution of people with epilepsy is very many young people and very many old people. And in the region where we are working, it's mostly prominent among young. So kids can have seizures. They will not be able to go to school. They can be demonized. People think it's contagious. And has really bad effects here. But on the other hand, if they can get the treatment, they can go to school normally, and many of them will then grow out of it again at a later stage, so they can have normal education and normal lives if we can treat them. So that is the problem. So how do we solve it, or what is our solution? So our solution is actually a affordable EEG machine equipment, so consisting of simple technology like this cap here that has electrodes on it, a slight box here that's an amplification box that connects to the cap, records the signal, sends it via Bluetooth to a mobile phone, and an app that then records the EEG. This EEG is then sent to a cloud solution to the other end of the country, where we can have people look at it, or another country even, right? And there are some challenges in doing this, and some of the main things that our solution solves is this low cost of acquisition. Our equipment is 1/10 of the price to acquire. So clinics that do not have a lot of money can get it. But that's typically not the worst part. Typically these clinics will actually be able to afford quite expensive equipment. But they don't have the technicians to run the machines. So they need to hire specialized staff to do the EEG scans. And they also need to hire specialist staff to do the interpretation of the EEG scans. And all of these things we are trying to solve. So the cost thing is, of course, we're making a low cost solution, but it also has to be easy to use. So it has to be so easy to use that we can take an existing nurse and give half a day training, and then they can do high quality EEG scans that can be used. And then this is an example of what an EEG looks like. Some of the different states, you can see the EEG is basically just brain waves here, right? And we cannot read thoughts, we cannot do all other kind of fancy things, but we can look at these things and see if people have symptoms of epilepsy. And here are some examples of what that looked like. One of the things that can complicate this is that EEG signals are very small electrical signals. So if patients do anything like blink their eyes, there will be very prominent signals in there. Or clenched jaws is a big thing also. That will give something that looks a little bit like this. And as you can imagine, if patients are nervous, they come into these sessions, they'll be tense. They'll tense up, and the signals can be filled with artifacts. In our part of the world, there'll be an EEG technicians looking at the signal as it comes in like this and say, oh, there's too much of these artifacts, now you should relax, now you should do this. These people are highly trained and are not available in this part of the world. Therefore, we try to assist this process in making a very sort of guided, user-friendly guide, but also in detecting some of these artifacts while we run the recording. So we say, okay, now that's actually too much noise. We can pop up a warning to the patient. This is one of the places where we use the AI algorithms. In such a EEG scan here, there's some things you need to do. You need to relax. You need to do facial exercises in the beginning. For example, you ask the patients to do the eye blinks, so you know what do these eye blinks actually look like. Then you can calibrate the algorithms to the precise patient. Also the jaw clenching and different other kind of things. We can do that in our guided exercises. We also have sort of a very nice smooth user interface that we spent a long time implementing. So I'll be happy to show you. I'll give you a demo afterwards. Looks good. Here's some of the impedance measurements. How well are the electrodes connected? Visual feedback for this is very important. Again here, the guided exercises. Clench your jaw, close your eyes, look straight ahead. Close your eyes. When you close eyes, there will be very prominent alpha waves, especially in the visual cortex, so you'll be able to see those clearly in the signal. All of these things we can use to assess the quality of the scan as it's coming in and give feedback to the operator when they're using this. Then in our app here, we also have the possibility of annotate things. For example, if we can see when you're the operator looking at the patient can see, okay, now they're actually moving their head. Then we would like them to move your head. The patient is moving their head. tell them to stop, but also annotate it so the person in the other end that's interpreting this can see, okay, this looks strange, but it's just a head movement. It's not actually an epileptiform discharge. Because there can be some of these artifacts can easily be interpreted. So we give the opportunity for the person annotating it to very easily give the feedback to the in the entire chain here. So we're testing our equipment all over the world. So up here we have testing in our own office. That's a usability test where we have our app and all these kind of things. So we have nurses come in with no previous training, running scans with our app, see can they get to the quality that we want them to in this, and they can. We're very happy about that. We just finished the test. We're running another one soon, and I'm recruiting volunteers. I have a slide later if you're interested. Next picture is in Philadelphia, the epilepsy hospital in Denmark. We are comparing the performance of our machine to the existing technology. This guy is in Bhutan doing scans in a study together with Harvard Medical School. Here we have the equipment in Kenya, where we are. That's our first market where we're testing it with nurses. I have super good feedback from all the hospital groups and potential customers there. They want to get this right away, and unfortunately, as this is medical equipment, we cannot sell it until it's CE marked or FDA approved, and that process is extremely long and cumbersome, as you also know. Yes. So we are in that process of getting our equipment certified. Also in process of acquiring customers, which is a little bit hard as we cannot sell them, we cannot take pre-orders. We really, really want to. I see on these fancy posters here there's something about the Pioneer Center for Artificial Intelligence also. And we are also somehow part of that. I don't know exactly how, because that's Lars that is responsible for that. But this is a slide I stole from him, that there's a 7-step plan for how this started as a very, very small researchy kind of project, got evolved through these 7 stages that I'm not exactly sure what are. But right now we are in this moonshot worldwide rollout of AI-based brain decoding. It sounds very good. This is what we're doing now, and we are right. So we are in Bhutan, we are in Guinea, in Kenya, using these AI methods to expand our capabilities here. So one of the things we really, really want to do is we want to build these ResNet 50 thing. The image processing has come really, really far by building all these models where you can have a baseline model that can interpret almost any image. And there's some self-supervised learning models that are built in this way. And I can go into much more detail. Lars can tell you this for hours also. But these models, we want to have one for EEG signals also. So one that once we have the interpretation of the signals or the collecting of signals, we can build these models. The way we are doing it right now is that we have interpreters in the loop. So we are recording the EEGs, sending them to the other part of the country, and there we employ people that are actually neurologists or trained to look at these signals, and they will do the diagnosis. So there's no machine learning or AI in the diagnostics part right now. But they're employed by us, they will do this in our system, they will annotate all the signals here in our system, so we get really, really good data back on this. And as we are in a part of the world where there's a lot of people that have epilepsy, we're rolling this out, we will get huge amount of training data in our system here. We are already getting some from our trial partners, but once we can go live, we will collect these things. So in that way, we'll be able to increase the turnaround time or decrease the turnaround time on the readings of the scans, decrease our costs on the interpretations, and improve the quality of our AI algorithms. And one thing that we put up here is that As we control the entire chain from acquiring the EEG to giving not the diagnosis but the diagnostic support report back to the patient, we can do these algorithms in our own system. So this way we don't need to have medical certification or quality assurance for these algorithms. The algorithms are not sold, they're not that internal tool for us to increase the turnaround time. I think this is one of the important lessons or learnings that I have from earlier also, that we need humans in the loop in all aspects. We need the operator to do the scans, we need to give feedback to the operators. When we do the interpretation and the diagnosis of the patients, we cannot do the diagnostics without the doctors. Not now, maybe in 20 years, but we need humans in this loop. We need to have the AI algorithms interact with people for them to be efficient. I think this is our part of our philosophy, that we need that thing. Luckily, that also helps us with the certification, because then we just need to certify the equipment and not the algorithms by themselves. Yeah, and this is some slides from our pitch deck here. What are the next things that we're going to do here? So epilepsy is a huge disease. The reason we start with epilepsy is because that's one of the main diagnostic path for epilepsy. EEG is the one thing you used there, and it's very clear the use case here. But it also has many other applications in sleep, home monitoring, like you're also doing. We could do that for epilepsy or for sleep, Alzheimer's, Parkinson's, all of these same diseases actually, right? But by measuring directly on the brain here. Yes. And now I want to see if I can recruit some of you nice people, either in the room or online, to our next usability test. Because as part of this getting approval for our medical equipment, we need to test that this works. We need to have nurses come in and scan actual, not patients, but people. And it's a good idea to have a wide range of people to scan here. So if anybody wants to have their brain scanned, you can get the results afterwards. It's not diagnostic tests, so we're not going to tell you anything about if you have epilepsy or any other diseases. We can also not read your mind, so there will be none of that. But you can see the scan. We can. It's fun. So yeah, if you're interested, then let me know, or write an email to Louise. We're also going to put posters up all over the place to recruit people. We need quite a lot of people for this. So, in short here, what we're doing is we're trying to bring this diagnostic, the EEG, to a much wider audience. And we do this by making it affordable to acquire the equipment, and by enhancing the usability with AI, so that the nurses can do the scans, get feedback, and get to a fairly high level of qualification without too much training. There's AI involved in that, and there's usability very much involved in that also. And then on a longer term, we want to automate diagnostic reporting to some extent, and use the AI capabilities in that also. And as we do, expand into more application areas. We are starting with emerging markets, simply because that's where most people need this. There's a huge demand for this. People are telling us, just come with this thing, so we just need to get it out there. Of course, on longer time scales, we could also imagine going back to Europe or the States, but for now, we're starting with Kenya. Thank you very much.
Thank you so much, too. Let's see what we have of questions in the room. Maybe you told us all there is to know about it.
Thank you very much. Really interesting. I see that you have multiple sensors around the cap. Do you consider the localization of each sensor in your algorithm to discriminate different type of epilepsy?
Yes and no. I mean, so there are several types of epilepsy. One is sort of the diffuse type, where it's sort of spread all over the brain, and you'll be able to see that. Another is the focal one. And the thing with the focal one is that it only appears in some of the sensors, right? So we need to have a sensor on the right spot to be able to capture it. But the signals look similar no matter where they are, but we need to know the location. Or we need to have a sensor close to it to be able to pick it up. So in that sense, yeah. And for the artifacts, also some of them, for example, the eye blinks, they will be more prominent in the front sensors here, because it's actually a muscle artifact, right? So it is, or the eye is a dipole, so it flips like this, and then it gives a very strong signal, and that's primarily picked up in the front ones. Jaw clenching is picked up here, of course. So yeah, so yes, so we use the location of the sensors, yeah.
Would in-ear EEG work as well? There's some companies that are specializing within development of EEG recording devices in-ear. Would that be possible in the future? Or does it depend on, like, exactly?
Yeah, so exactly. So the problem with the in-ear EEG is that it's not covering the entire head, right? So the EEG signal is not traveling very far from the source. So some of the diffuse epilepsy, you'll probably be able to pick that up with the in-ear. The alpha waves or the slow movings of the brain. But if there's something's happening on top of the head or on the back, you will not be able to see it on the in-ear EEG.
Thanks.
Thank you very much for good talk. Regarding the AI, you didn't go so deep in that, and I'm thinking about last talk we were hearing about sound processing and using AI there, and they took out some of the difficulties compared to if you do a picture analysis. You kind of have all the data. This is distributed over time. Can you say something about the pre-processing needed to get it into your AI model? Extracting what features you are extracting from the signals.
Yeah, so there are several approaches here, right? So the ones we're doing now is very much based on these temporal and spectral features, so spectrograms basically of the signal. So we block that up, and most of the things we are looking for, they happen on a maybe sort of 1 to 30 second time scale. So we can make sort of blocks of that, and then extract the temporal spectral features of that. And there are some frequency bands also. For example, the eye blinks are sort of approximately 1 second or below that long, so we can see those in there. So that they have a very strong spectral component, but also energy component. So those are some of the things we're doing when we're doing sort of the more classical feature extraction and then machine learning things. But then there are these, for example, the models where we are going into the image domain. That so a spectrogram can basically be considered as an image, and each channel can be one color channel in an image. So we can stack the color channels. So we have 27 electrodes. So instead of having an image with 3 color channels as we do for normal images, we can have an image with 27 color channels. Then we can run the exact same algorithms on top of those images, and then do all the deep learning approaches here to extract what we want. And then there's all, I mean, I can just roll on. There's also these are the transformer approaches, for example, like in sound and in natural language modeling. These transformer models where you can have these attention mechanisms. So you can actually process quite a lot, you process it sequentially, but you keep the attention mechanism to back to the things. There's a model for EG now called Bender that's being developed that is basically building on the same things as the language processing models. So we are also looking into these things. So I don't know if it was the Avenir guys that talked to you last time about. Okay, no, so not okay. Yeah.
Do we have more questions in the room? Do we have any questions online? No. Well, in that case, I think it is time to thank our speakers very, very much for 2 very inspiring talks. Let's give them a big hand of applause. And I'll just switch to, do we have, there it is. So this is one of the advertisers that I'd like to end on. We have upcoming talks on November 10th, where we're going to have a visit from Metro Nextbridge. They're going to talk about due diligence and about natural language processing. So you have something to look forward to there. Also on December 1st, we actually have Avenir, as you just mentioned, coming in and joining us together with Force Technology. So great talks coming up. If you have ideas for speakers you'd like to hear, if you'd like to nominate friends of yours, colleagues, or yourself to give talks here at Applied AI Lunch Talks, please do reach out. My email is in the bottom here. It's camjen@dtu.dk. And we take nominations. I think we have the first meeting with, among others, Lars Kai, in mid-November. So please send them our way. Another thing that you mentioned too was great input about the whole regulatory process and how difficult it is to dance with for people, innovators, whether it be startups or corporations that are trying to bring AI solutions to have impact in the world. And at the Digital Tech Summit, which happens next week, if you're here live today or watching the live stream, you can join it in the Bella Center in Copenhagen on October 26th, 25th. 25th is the day that we have the super session about how to navigate those challenges of getting AI solutions applied in the health sector. So it's 11 o'clock, October 25th, and I hope to see many of you there. And let's give our speakers a last round of applause, and thank you guys for joining us.